Good morning, everybody. And thank you, Seem, for a kind introduction as well as the invitation. It's a real pleasure to be back at EKA and see so many friends and familiar faces. So today I will be talking about some of the work we do in my research group around developing analytic frameworks and tools for better city design. And I'll start out with a few reflections on the theme of this conference that Seem has put together. The idea of building systems is an interesting one that I think truly crosses the different scales of built environment design, from all the way down to material microsystems to large metropolitan and urban systems. Broadly defined, the Oxford Dictionary tells us systems have to have a set of connected or associated counterparts who work towards some kind of a common goal. I think when it comes to cities, this analogy is indeed a useful one, since there are indeed many different kinds of systems in cities. Think, for instance, about a place-based system of a community development to improve a particular neighborhood, or a system of real estate in a city, or a system of mobility and transportation, and so forth. So when we look and ask the Google Ngrams, when did this word systems actually come about? I think it's also telling how our kind of mind frame of thinking in systems is very much influenced by philosophies of our times. The first increase of the word systems seems to have happened during the Industrial Revolution. This is after Newtonian physics has already been invented. This is during the construction of large-scale manufacturing systems that boost national economies and transform economies around the world. And then more notably, and more recently, in the post-war era, the Cold War systems thinking, largely promoted by the Rand Corporation in the US, but also various kinds of military-industrial complex systems, affected how systems thinking really entered all forms of organization and entrepreneurship and company lives. There's, in the field of urban planning and urban design, these post-war developments in systems thinking, propelled by the works of likes of Alan Turing, Norbert Wiener, John McCarthy, Marvin Minsky, Herbert Simon, etc., had profound influence on how people thought about systems in the built environment and also systems in social settings as well, including in policymaking. At MIT, John Forrester coined the term systems theory or feedback loops, where he argued that this kind of idea of systems theory that's fundamental to cybernetics is also applicable to cities, that cities indeed show the general characteristics of a complex system. And indeed, there was a lot of work to tie systems thinking to urban policies, urban strategies, and also spatial planning at the time. Likewise, Herbert Simon, who has written Sciences of the Artificial, applied his systems thinking analysis of problems to policymaking. He developed a famous 7-point methodology for evaluating alternative policy scenarios for human systems, and that was incorporated to public policy making, described in a famous article by Stokke and Zackhauser. This is a way of analyzing how alternative policies for similar things, for instance, alternative plans for a neighborhood, alternative transportation proposals, alternative development proposals for a city, may be evaluated in a quasi-scientific manner. And when we think of them, their applications in a city, one could argue, as some have, that perhaps a city really is a system of systems. that it includes many of these smaller systems that are, whether they are place-based, neighborhood-based, that are thematic or topic-oriented, as in one city department working on one set of issues with the budget and staff. And these subsystems all interact with each other and form something that we might call a city. For instance, there are housing markets, as I already mentioned. There are commercial real estate markets. There are transportation and land use planning systems. There's architectural systems thinking. There's also broader environmental systems such as climate change, social inequalities, and so forth. So in a way, this analogy as a city as being a system of systems, I think is somewhat more accurate than some of the other analogies that have been used. For instance, cities have been compared to machines or organisms. And I think those analogies, even though quite popular, are perhaps less acute because a machine typically has a purpose. It is something that works to a set of parts that work in cohesion towards a very well-defined goal, whereas cities really don't have such well-defined goals. And similar to organisms, I mean, organisms, I think, too, have been used as an analogy for cities, and that, too, I think, misses the point that in organisms, there are systems that keep a body alive and generally don't have all that much free will and kind of unpredictability in terms of how they function, whereas cities are full of unpredictability. So this more loose definition of systems, I think, actually captures in a more apt way how cities actually work. Jane Jacobs, in her famous book, The Death and Life of Great American Cities in 1961, has described a city as a organized complexity. She says that cities happen to be problems in organized complexity, much like life sciences or biological bodies. And she argues that there are several interrelated parts and systems that each affect one another. And I think what's particularly interesting and also challenging for studying cities in that manner is that interdependence between systems is what makes it really complicated to understand how any intervention or change that is man-made in a city can affect the outcome. Because that one intervention doesn't just affect some other outcome variable or dimension on its own, but it enters into a complex environment of interacting systems where everything depends on everything. And that's precisely what makes it really hard to plan cities, and also really interesting to study them as a discipline. Many dominant systems that we have in urbanism are not really configured explicitly to make cities a better place. In capitalist systems, many systems, in fact, operate to do what capitalism is supposed to do, that is, to grow capital. Let me use an example. The same Norbert Wiener, who was part of the cybernetics movement in the early post-war era, dabbled in urban planning to some extent during his years at MIT. In fact, the very idea of urban ring roads comes from Norbert Wiener, who is a cyberneticist. And he proposed this idea in the 1950s as what he calls life belts. This is the era of warmongering, of nuclear threats after the Second World War. And as the nuclear armament competition was underway between the Soviet Union and the United States, the nuclear threat really disrupted how people thought about cities in the US. And the problem was that dense cities that were predominantly known on the East Coast, but by that time increasingly across the US, were really volatile to the nuclear threat. Imagine, for instance, a dense city like New York or Washington, D.C. or Boston. And so these so-called life belts were supposed to be large vehicular ring roads connected through highway interchanges that would rapidly funnel people out of these dense city centers in the case of a nuclear threat. In retrospect, many politicians and observers at the time noticed how ill-conceived and unrealistic this idea is. One Senator, Pat McNamara, in the US Congress, said that it's inconceivable, even on a normal day, to imagine millions of people trying to flee a city, even with one accident causing a backlog, let alone under alarming news of a nuclear threat. This would never be an efficient way of actually doing this. But it illustrates, I think, that systems thinking in a sort of fairly narrowly defined way can lead to some fairly problematic proposals about the city when we sort of narrow the problem down to a particular system of transportation, which is vehicular transportation in this case. Along the same lines, in the post-war world, this kind of systems thinking and nuclear dispersion idea led to some pretty wild plans for reconstructing cities. A German planner, Ludwig Hildesheimer, who came over to the US together with Mies van der Rohe, came up with this idea of, well, actually, he did not come up with this idea, but he continued this idea of neighborhood units, shown here on the left, which is actually an idea that dates all the way back to the early 1900s. It grew out of the Garden Cities movement. But these are supposed to be self-contained units with cul-de-sacs where you drive in with your vehicle and you park away on one of these side streets. And the whole idea is that you minimize the opportunities for people to cross streets. He famously professed that kids can walk to schools in such places without ever needing to cross the road. In reality, this was also very much a system for facilitating traffic. Both Norbert Wiener's ring roads, the so-called life belts, and Hildesheimer's plans for these autocentric, sprawling built environments were really part and parcel of a framework of thinking at the time, which was, how could we build environments that accommodate more cars? How could we build cities so that transportation largely happens in a private automobile? These two plans on the right, this is Hildesheimer's version of rebuilding Chicago as a really low-density, sprawling system of these cul-de-sacs, and here's his vision for rebuilding Manhattan. These were not merely naive ideas at the time, but indeed had some pretty profound influence on how things turned out. If you think about the system of autocentric cul-de-sacs, this is exactly what most of the suburbs in the United States got, and now also most of Europe outside of traditional urban cores. Peter Norton, who's an urban historian of the automobile, has written extensively about this, and in his book, Fighting Traffic, The Dawn of the Motor Age in the American City, he calls this system of automobile manufacturers, automobile vendors, insurance companies, oil companies, and highway construction companies collectively as motordom. It's a collective of economic actors who are interested in profiting from the sale of automobiles in the United States, and who did it with jubilant success over the 20th century. And he divides this kind of era of the 20th century motordom into three phases. Phase one actually predates these plans from Hildesheimer or Wiener, etc. Phase one happened roughly from the moment that the first Model T was sold in 1907 by Henry Ford, all the way to the Second World War. And this is the key to enabling the kind of dominance of automobiles in American cities at the time, was reconceiving what streets were for. In a famous quote, the editor of Engineering News Record, which is a large engineering magazine in the United States, its editor, Edward Martin, concluded that the obvious solution to American cities lies in the radical revision of our concept what a city street is for. What he's talking about is moving away from the 19th century street where anybody can cross anywhere and it's a big messy environment where people kind of self-organize and where some public transport runs, some horse cars, lots of pedestrians, towards a highly regulated environment that puts automobiles first. And so in the 1920s, the first traffic ordinance in the United States is passed in 1924 in Los Angeles. In fact, a traffic lab is started at Harvard University a year after that, and very quickly regulations are rolled out that are adopted by states and cities across the nation to ensure that there are very strict rules of how streets can be used for automobiles. All that ensures that there is a rapid growth in automobile sales and adoption. And so Peter Norton makes the argument that whereas there kind of a common myth is that people of the time sort of naturally went from the inferior technology of the horse car and public transit and streetcars to the superior technology of vehicles is a myth. That the evidence shows that there were major fights against this trend, and people didn't necessarily choose the automobile over other urban mobility systems. But in the background of all this, there was a large concerted effort, including automobile clubs that sponsored campaigns, criminalized jaywalking on streets and so forth, to make sure that the environment is configured for the expansion of the automobile. The second phase of this happens during this post-war era of nuclear dispersion, and this idea of building cities for defense with these life belts and these low-density circulation systems really mobilizes the Congress to allocate vast amounts of funding to build roadway systems. So famously in 1956, the Federal Highway Act or Interstate Highway Program is established, which allocates huge sums of money to build a national network of highways. 41,000 miles of highways, which is about 66,000 kilometers of highways, that would connect all major cities to each other with a continuous highway network. The federal government says to the cities that if you participate, and mind you, this is in a kind of a late 50s, early 60s period where there's kind of a little decline after the initial post-war economic boost, so cities are struggling at the time, and the federal government says if you build highways in your city, we will pay 90% of the cost. So most cities take the bargain, and we famously get a huge wave of highway construction through cities. And again, Peter Norton argues that this is part of the system of Notre-Dame. This was the second large wave of policies that facilitated the sale of automobiles and the expansion of Notre-Dame, automotive infrastructures, and vehicle adoption in American cities. Whereas by the early 1940s, late 1930s, the automobile sales in America had actually stalled because in dense city environments, people were not buying cars, and there's really interesting literature showing that automobile companies thought this was a major problem. People are not buying cars in Chicago. People are not buying cars in Philadelphia because they have better options, right? They can ride the public transit system, they can walk to places, and they said, we got to do something about this. And so this whole world of warmongering and kind of creating the fears that would then build public support to build highway networks was very much part of that system of ensuring that the trend of motorization can continue. And then, of course, after 2000s, we've again come to what many publications call peak car ownership, peak oil, and the kind of Norton argues that Notre-Dame has invented the next solution. He always says that the solution is about 10 years away, that always the kind of a perfect world of universal transportation, no traffic jams, etc., is just about 10 to 20 years away. And now the solution lies in automated electric vehicles. So if we just wait 10 more years, everything will be solved, right? So it's the same story from the 1920s or the post-war era and so forth. So this is an example that I wanted to use as one fairly complex, elaborate system in cities with lots of large economic actors that has fundamentally transformed cities throughout the 20th century. It has transformed cities that looked like this in the early 1900s, right about the time when Model T by Ford was released, 3 years after, 3 years before these photos. And this is what downtown Los Angeles looked like. This is what Boston looked like. And notice on the ground all these tramways, all these streetcars. In fact, in the early 1900s, Los Angeles, which is now known as the car capital of the world, had the longest network of public transportation systems anywhere in the world, more than London, Paris, or Tokyo. All of that, of course, is no longer true. And 100 years down the line, we get this. So this is the kind of example that large systems don't necessarily work to make cities better places. They work for other purposes too, like making a profit. But we've come to a point where this is generally thought as unsustainable, something that we cannot continue doing because we are hitting limits to growth. We are hitting limits to the amount of emissions that cities produce and the amount of energy that cities demand to operate. So we need to move away from this model of planning cities around motordom, as Peter Norton describes it. A few examples of how city design is directly related to this. I've plotted here data that I pulled on CO2 emissions from the transportation sector in the US across American cities. On the x-axis, I show CO2 emissions per capita, so per inhabitant for a typical person in a city. And on the y-axis is the population density of that city. What's fascinating to me about this are two things. First, as largely already described by the work of Newman and Kenworthy, there is this exponential pattern to this chart, meaning that really dense cities tend to exponentially consume less or produce less emissions than low-density sprawling cities. And second, how wide the x-axis is. If you live in a city like Boston, an average inhabitant produces 2.6 tons of CO2 emissions from transportation alone. And that same average person, just by the fact of living in a city like Houston, Texas, produces almost 10 tons of CO2 per capita per year. This is almost a fourfold difference. Just think about it for a minute. The city that we live in causes each inhabitant to produce 4 times less CO2 per year. Not because they're different people, not because they're inherently different species, but just the way the city makes them move. And Boston is no poster child. It's still fairly out-oriented. We have much denser cities in Europe with much better public transit systems than Boston. And of course, this has to do with the kinds of cities that we're comparing here. Boston is a much denser environment. It's on average over 5,000 people per square kilometer, whereas Houston is only about 1,400 per square kilometer. So urban form, land use patterns, and density have everything to do with this difference. And interestingly, it's not only this story of transportation emissions either. I've put up on the same chart a different outcome variable. In this case, this is energy consumption per year per capita. This is electricity, not CO2 emissions. The picture is broadly the same. Residential electricity consumption also follows this exponential trend. And this is interesting because this is due to the fact that the building typologies that people live in is intricately related to the transportation systems that we assume them to travel by. In a city where everybody travels by car, you will get the single-family homes with driveways and large footprint houses that have 4 walls and a flat roof. And from an energy perspective, that has a very different outcome than people living in multi-story structures of mixed use in denser city centers. So a typical person in Boston consumes about 2 megawatts per year per person, and one in Houston about 4.7. So difference over 2. And that's not only the story of the United States. I just happen to have good data available of these systems in the US, but it's also a story right here in Estonia. I've gotten some data from Estonian Energy and show that energy consumption per year per square meter of buildings very much depends on the building typology. In low density single family homes, we get much higher consumption per square meter than we do in multi-story buildings. So it's the same idea that transportation systems and building systems are interrelated to each other. And how effective or sustainable the built environment is depends on both, because transportation is responsible for roughly 1/3 of all CO2 emissions in a country, in an industrialized country, and buildings are about another 1/3. Those two systems together are responsible for the vast majority, 2/3 of all CO2 emissions. So how we design cities, how we design the environments we live in, has everything to do with the emissions and energy demand that we're currently struggling to curtail and solve. To the point where the IPCC reports by the United Nations now officially promote that the kind of city that one builds has the largest possible positive impact on climate change. So if we can build more cities that are transit-oriented and walkable in the world, then that is probably the most effective way of eventually tackling climate change. And these benefits are not only from the transportation sector, but across the board, as you can see here, also health benefits, water, construction, land, all of these have better outcomes in denser, more pedestrian and transit-oriented cities. So what I want to emphasize is that we need to ask ourselves this question: what systems do we need to guide new urban development and growth towards more walkable and transit-oriented built environments? And we must acknowledge, of course, that we come at this with a huge trove of legacy systems that we're still stuck with from the 20th century. So the shift to a different alternative is not easy. But nevertheless, we must try. And I think in the following half of the talk, I want to illustrate some of the research we are doing in my research group that try to introduce new frameworks of thinking and methods for spatial planning and analysis that help us get more towards this type of a city, where it's not overly dominated by the automobile, but it has a multimodal, more equitable transportation system, and quite importantly, besides these kind of trunk systems, has enough density and land use diversity to support various kinds of amenities and non-home work destinations around places of residence and places of work. And it has a whole series of important benefits that address current urgent challenges of urban planning and design. Not only sustainability and decarbonization, but also public health, because when people move more and are spending more time outdoors, and not only physically do they get better exercise, but also meeting people in denser city environments has veritable mental health benefits as well, and so on. So I want to share some of the frameworks and tools around this theme of the urban network analysis framework that I've been working on for now close to 15 years. And it's in part a set of software tools and methods, and in part a series of applied examples of where we do analysis in a given city to help understand its non-motorized mobility better. There's a plugin for Rhino that was developed together with Raul Calvo, who's sometimes teaches here at EKA too, and who spent some time with me in Singapore. And then most recently we have a open source Python package called Medina for doing these things more automatically. And the premise of all this is that in order to model, understand, and analyze built environments from a pedestrian perspective, we need to be able to represent them as such. And the kinds of tools we have as a legacy of 20th century systems are really not configured to do that. For instance, transportation models typically operate with traffic analysis zones. These are pretty large areas or zones between which traffic flows are modeled by car. This is not how people perceive a city. Even with one single traffic analysis zone can be a whole experience of somebody walking around and being meeting all sorts of environmental stimuli, other people, and experiences. So we need to represent cities as pedestrians actually perceive them. And I believe this sort of network framework is well suited for that. We can represent individual buildings as networks, streets and kind of indoor-outdoor relationships, all the way to districts and whole metropolitan areas as networks. And that's something that's quite suited also for various CAD and GIS systems, where we can have geometry objects that represent origins and destinations or obstacles in networks. They can have all sorts of properties associated with them, and then we have geometric networks that can be two-dimensional, three-dimensional, and so forth. So I'm going to demonstrate first how we use this framework to understand the relationship between city design and pedestrian mobility. This has been a question that's been quite interesting to architects and planners for quite some time. Famous diagram by Louis Kahn of Philadelphia on this image, where he tried to diagram the flows of people in the city. And quite famously, a number of notable 20th century urbanists have worked on the problem or described the problem of the activities that occur in between the buildings on the streets by pedestrians. For instance, Allison and Peter Smithson famously coined this term, the charged void. The charged void basically describes the space between buildings, which they say is charged with energy, which can join up with other energies, which can define the nature of things that might come, anticipate happenings. But they also emphasize that it's a capacity we can act and feel upon, but cannot necessarily describe or record. In other words, they're saying that every good architect knows that the way buildings are configured in a city will impact the life between the buildings, but that's something that we can't directly analyze. It's something that we can intuitively kind of guesstimate and describe. Similarly, James Jacobs famously described the same phenomenon as the sidewalk ballet, the kind of social interactions that take place on streets, or Jan Gehl describes it simply as life between buildings. So in this work with the Urban Network Analysis Framework, in my work, I do think that we can describe this much more accurately, and I do think we can analyze what happens between buildings by non-motorized street users if we put our minds to it. So I'm going to use an example of a large model of pedestrian flows that we've recently built for New York City. The way it works is that we analyze various kinds of trips that are expected to occur during different periods of the day, during the morning peak period, during the lunch period, or during the evening peak period. And for each trip type, there is a series of kind of assumptions that the model can handle, which describe, in this case, this is one particular census block in New York, which is then divided into 4 frontages, and the kind of trips are going from each frontage of the block, and they're going to subway stops. So this is one particular trip type from homes to subway stops. And people are not assumed to walk the shortest route, because generally they don't. We know that from the pedestrian route choice literature. And there could be many destinations. In this case, this is one single subway stop, but there are 2 entrances, so the flows are somehow split with a particular way of modeling the probability of that. And if we then scale that up to all subway stops that one block can actually access in a reasonable walkshed, in a 10-minute walkshed around it, then we keep the amount of trips constant, but they're just proportioned and routed to different kinds of destinations. And then we can do this across the whole city at a larger scale and get fairly a detailed understanding, or estimate in this case, of pedestrian flows for that one type of trip. We then, using Medina and the kind of more automatable framework for this, can model trips between all sorts of land use pairings, from homes to subway stations, homes to bus stops, homes to parks, jobs to restaurants, jobs to subway stops, homes to schools, and so forth. So it's a whole matrix of different kinds of trips that we know from travel surveys typically occur during the different peak periods. We don't attempt to model every possible trip, we just model those that we know dominate during the different periods. And using Medina, this can all be automated with what we call a pairing table. So you feed in a pairing table, and these are all computed in the background. And so as a result, we get these different kinds of estimated flows. So these are trips between businesses, these are from homes to businesses, homes to jobs, homes to metro stations, homes to parks, homes to schools. These are from jobs to amenities, jobs to metro stations, parks to metro stations, etc. So at this point, these are all still estimated flows, not actual flows. And then the model is calibrated with actual pedestrian counts from a set of locations in the city. In New York, we happen to have roughly 1,000 locations where pedestrian counts were available in the city center. And these are the so-called ground truth. We know accurately how many people actually walked at a handful, or in this case, 1,000 locations in New York. But we use this calibration data to then describe how we can model the full behavior of dominant walking trips and expand or extrapolate this understanding to all streets in the city, effectively hundreds of thousands of street segments, over 300,000 street segments in New York. So we do this by using the actual count data as the dependent variable, or as something that we try to explain through the model, and then calibrate the model, in this case using a machine learning model calibration technique, which fits the predictions against the actual observed foot traffic and achieves a certain kind of explanatory power. So the model is what we call a 80-20 split five-fold cross-validation technique, which basically means that we train the model on 80% of the data, then we predict the remaining 20%, and then we randomize this 5 times around until we get the kind of best-fitting model. And then it forecasts trips for weekdays and weekends, and during the AM, the lunch, and the PM periods. And generally does a pretty decent job, especially for weekdays where the fitting is very accurate, and then the tests on the unseen data is about 76% accuracy, or 71% accuracy, and 73% accuracy. As a result of this calibration, we essentially get a model of foot traffic across all of these trip types. Not one trip type, but this is now this kind of mixture of all trip types together. This is the calibrated model. This is our best estimate of, this is for the evening period on weekdays, of foot traffic in New York City during the evening peak hour from 5 to 6 p.m. And if we zoom into a particular area and compare it against actual foot traffic counts, then we see that it's not perfect, but it's pretty decent. For instance, there on this segment here, these blue labels, they are actual counts that the Department of Transportation collected from the city streets, and the white labels on the yellow segments are model predictions or estimates. So we see that, for instance, this segment actually had 1,550 pedestrians on the crosswalk during the evening peak. Our model estimates 1,330 something on that. It's not perfect, but it generally does a pretty good job. And across all time periods, the explanatory power is fairly strong. So in each time period, it's over 90% correlation between the predicted and the actual foot traffic. So why is this useful? What do we do with this? First of all, as I mentioned, the pedestrian counts are available at some locations, like in every city, but the model allows us to extrapolate that to the rest of the city. By understanding the dynamics behind those counts, we can estimate foot traffic on virtually every crosswalk or sidewalk segment in the whole city. And that is quite useful because it can help allocate scarce taxpayer resources to the places where they affect the most people. So if we want to make sidewalks better, public spaces better, it helps to understand how many people that would affect on a daily basis. And second, it also can form a pretty important denominator for all sorts of hazard data for pedestrians. For instance, if we look at exposure to traffic crashes, or to urban noise, or to even heat during heat waves, understanding of how many people move in particular place in the city can form an important denominator. I'll shortly illustrate that further. And then perhaps even more importantly for urban design and planning, having a model behind the picture can also become very powerful as a way of forecasting how future interventions and changes in the city will impact pedestrian flows. And I'll also show that. So to the first point about including a denominator, this is an image of the 100 worst traffic crash intersections in New York City over a 10-year period. So this shows where, by color coding, where most pedestrians were injured by cars in New York City. You can see a fairly important peak in Manhattan, where there's a lot of crashes all the way from Midtown to downtown in this area, the highest concentration in the city. If you think about it for a moment, it's probably obvious that that's also where most people walk in New York. This is the highest pedestrian volumes, places like Times Square, right? Now, if we take this data and divide it through, or so-called normalize it by these pedestrian volume estimates I showed from the model, we get, we get a totally different picture. Manhattan is no longer even on the map, because if we say crashes per pedestrian, then it's a different story. This is far lower crash probability. And both of these pictures are important, by the way. On the left, we describe the total number of humans who are in a crash. On the right, we describe the crash probability, which has to do with also how many people are exposed to the traffic. That's the volume of pedestrians. And so, in fact, many other areas of the city have higher probabilities of a crash because they have very low pedestrian volumes, but whoever walks there is subject to more danger, like in Staten Island, parts of eastern Brooklyn, and notably Bronx. And then I mentioned the second important use of such a model is to be able to also forecast how urban design interventions will impact pedestrians in a city. So I'm going to briefly show that and conclude. This example comes from a study we did in Beirut, Lebanon. It really pains me, by the way, to see what's happening in Beirut right now. We were there 2 years ago with our research team doing this project, and our collaborators are still at the American University in Beirut. This region has been through so much suffering, but to see yet another war underway is heartbreaking. So this study was done after the Beirut blast of 2020, where there was the largest recorded civil explosion in the port of Beirut up here. And we collaborated with the local university and a DAR corporation to do a study of neighborhood improvements in the blast-affected areas over the last couple of years. And the process for the study was roughly this, where we again started by developing a pedestrian model. So we collected data, we did preliminary flow estimates like I showed in New York, and then we calibrated the model on actual pedestrian counts that we conducted in Beirut. And then we used that model to examine how urban design interventions that were proposed for the neighborhoods would impact pedestrians. So this is the calibrated model for pedestrian flows during the evening peak period in Beirut. Again, calibrated on the actual pedestrian counts and involving multiple types of pedestrian trips during the evening peak period. And then we organized this sort of co-design workshop with stakeholders from neighborhood associations, city government, universities, and companies in Beirut. We started with walking tours to kind of firsthand experience the conditions of streets in the city and to let the neighborhood folks illustrate to the rest of the crowd what they thought the main issues for walkability in those areas were. And then we had a kind of a 2-day design charrette where folks came up with their own ideas of what needs improvement, what are the most critical interventions that are needed to make these neighborhoods more pedestrian-friendly and walkable. And we then, as a research team, took these findings and digitized them into scenarios. So we had this baseline model of calibrated foot traffic flows, and we needed to translate urban design proposals into that model so that we can understand or estimate how these design changes will impact pedestrian flows in the city. And that's what these scenario analyses will illustrate. So this is one example. This is a kind of a concept map of various urban design interventions that were proposed as part of one of the scenarios. We analyzed several scenarios, in fact. This is a scenario where some key streets in the area, like Groot Street, Pasteur Street, etc., were improved with one lane of parking taken away, sidewalks widened, some new ground floor amenities zoned for the area, some parks opened up that have been locked up since the pandemic, and 2 new footbridges to this district called Karantina over a highway. So those were put into the model. They were also kind of designed or analyzed by the collaborators we have in Beirut for this. This happens to be the example of one of these footbridges, which is in terrible condition today. So they imagined a better version of that. And some of these really clogged streets by traffic, how they could be improved by giving space back to pedestrians, and some of the ground floor business improvements. And then as we put these scenarios quantitatively into the model, we could estimate how they would impact pedestrian trip generation, that is, how many walking trips are likely to occur in the neighborhood, and pedestrian trip distribution, that is, where are these additional walking trips distributed. And we could do this across the different trip types. So we could estimate that, for instance, there would be amenity trips, which is trips between businesses, would grow by 16%. Overall, in this particular second scenario, which involved quite a lot of interventions, we estimated about an 85% growth in foot traffic if all of these interventions were actually materialized. And then the model could also illustrate where the change would spatially go. So this is the baseline foot traffic model today in this area of the city, and this illustrates in blue segments where net positive growth would happen, and in red where net negative growth would happen, meaning where additional pedestrians would be moving due to these specific urban design, street design, and land use interventions. Why I'm showing this is that thinking back to the kind of system of systems idea, what cities do today when large projects are permitted, this is a kind of an international system, is that when large projects are permitted, they require what we call environmental impact review. So you have to analyze how the proposed project has environmental impacts on the city or the environment around it. And a very important part of this environmental impact review is traffic impact assessment, studying how the proposed development impacts vehicular traffic. Can the streets accommodate it? And usually what this is a model of traffic flows estimated for different intersections and streets. And if the streets cannot accommodate the additional traffic that the project would cause, then mitigation measures are required. In many countries, the developer pays for these mitigation measures. They can be signal readjustments, they can be road widening, extra parking provisions, extra turning lanes, and so forth. And this is a kind of a hidden system that continuously transforms the built environment even today, even during the sort of critique that we say we're post-peak car, we need to plan cities differently. We have these legacy policies that are in the systems where development impact assessments propose mitigation measures that accommodate additional vehicles in the built environment. And it's a kind of a vicious loop that keeps going around and around with every new large development, making sure that streets can accommodate more and more traffic. Something that also Tallinn does, right? Tallinn has historically had in road projects this kind of like safety factor of something like 20% provision for new growth in future traffic. And I fundamentally think that the kind of example that I show from Beirut portrays a different system thinking where we should be instead analyzing how new developments impact pedestrians and transit. And so instead of these traffic impact assessments, shouldn't we have something like a pedestrian or transit impact assessment systems where we systemically analyze how every new real estate development can contribute to more sustainable mobility rather than more traffic on city streets? And so let me conclude by a couple of points. First, what I try to emphasize is that city design plays a really central role in affecting energy emissions, public health outcomes, and also social equity outcomes in cities. It's a dimension that oftentimes is lost in the political debates. If you read the news, the green movement oftentimes talks much more about electric vehicles or electric home appliances, but how we build our cities fundamentally has the largest long-term effect on the outcome. And I think we need to recenter that in the debate. Second, pedestrian and transit-oriented environments really are, I think, the best solution we have on the table for long-term success with all of these outcomes like decarbonization, like public health and social equity. So it's a model of a city that we need to think about what policies, planning, and strategy systems will help us get towards that outcome. Third, it's important to actually collect data on the things we care for. Like Jan Gehl always emphasizes, we must count what we care for. Not just count the traffic like all cities do, but count the pedestrians, count the cyclists, count the public transit ridership, because that's the outcome we really want to model and improve. Fourth, the kind of models we do must represent the environment through the eyes of the user, not kind of accommodate the traffic model for things that it cannot do, but really have models that describe how pedestrians or cyclists or transit users perceive the built environment. Fifth, that the kinds of systems that I showed at the end, the kind of assessment of how does new real estate development or project impact the non-motorized flows, is something we need to actually incorporate into policy making. Not just a kind of a one-off project, but something that can be done automatically for every sizable development, so that over time we start seeing success. And finally, I'll argue that we also need to think about new policies and new regulations that would ensure that every new development or project we build in a city makes a positive improvement or addition to the pedestrian environment. And the analogy I want to just use for this is think for a moment about parking regulations in cities. For close to 75 years, cities have been requiring that new housing projects, new commercial projects build parking that is connected to city streets. So there's like a continuous system from the feeder roads to the private parking lots. There's a continuity there. Think about how could we do something like that for the pedestrian realm? That every project must add a little bit of high-quality pedestrian space that is connected to the sidewalk, that is connected to the rest of the neighborhood. Think what would happen if that would run for another 100 years, just like how the parking regulation transformed cities over 100 years. This is the hidden force of policies beyond individual architectural projects that can really have a transformative effect over a long period of time. Thank you.